So we continue with our Holt-Winters exponential smoothing and move on to the second scenario. So what was the second scenario? Well, what was the first one? The first one that we already dealt with was all of them are additive, so nothing to worry about that part. The second part, so the first scenario that we dealt with had the trend constant. That is, the data did not vary across time. It was more of random fluctuation that we modeled. It didn't have seasonality. So the second one, the only difference between the first and the second is that the trend is going to vary this time. It's going to either increase or decrease. It still is not going to have any seasonality. So moving on, a good data for such a scenario, that is, which has a varying trend, which has a trend component, but no seasonality, and it's an additive series, is again the annual diameter of women's skirts at the hem from 1866 to 1911. Again, like this data might not sound very businesslike, but this is publicly available at Rob Hindman's website, and Rob Hindman has a lot of time series stuff on his website, so you can always look it up at your leisure. And after this lesson, after this module, I'm sure you are going to find most of the stuff on his website pretty familiar, and so you are most welcome to browse that website and check it out for yourself. What are the things that perhaps I haven't covered lies out there in his website. Anyway, so coming back to our exponential smoothing, so we are going to deal with annual diameter of women's skirts at the hem. Our start date of the time series is 1866, our end date is 1911, and here, start here, whatever. So first thing first, what do we need to do? We need to read in the data. You can read it directly in from the URL. You need to convert it into a time series, and of course, like, you cannot forget about plotting the time series. You have to plot the time series. You plotted the time series. So what does it look like? You can see from the plot that there was an increase in hem diameter from about, like, there's an increase in hem diameter over here. I mean, that's pretty common sense also, right? We have all watched classical Hollywood movies, etc. Then women preferred to wear skirts with big hems, large hems. And then the hem diameters comes down and down and down, and these days, like, as we progressing towards more modern era, if someone walks out on the street with such a large hem, it will perhaps be totally weird. So the hem diameters have come down with time. So that's easy to understand now. So this definitely shows a trend. The level of the time series, that is, at any time point, the mean of the time series is different at this time point compared to this time point. The variation is different between here and here and here and here. So this data basically shows trend. It's increasing followed by decreasing. That's the trend. Cool. But it has no seasonality. It's not that some part of the year it goes up, then comes down, and again goes up the same time next year and comes down. It has no seasonality. So it shows trend but no seasonality. So what do? We use the Holt-Winters function, and we feed it our time series data, skirt series, and we model it. Now I'll explain these parameters gamma. Okay, let's have a look at what we did when we dealt with the scenario before. When we dealt with the scenario before and used the Holt-Winters function to exponentially smooth the data, we said beta equal to false and gamma is equal to false. And what do these terms relate to? Let's go back in a slide to the various ways to deal with time series. So here is our exponential smoothing section. Let's follow the equations. Now if we look at it, when we did single exponential smoothing, that is the first scenario that we have dealt with in R, that is constant trend, no seasonality. This was the equation. Okay, so it's alpha times current actual value plus 1 minus alpha times last period's value, and that gave us an estimate of the current. That gave us the current estimate. So we had just one coefficient alpha in single exponential smoothing. So when we dealt with the first scenario in R, it is single exponential smoothing. So you need just alpha. So you tell R that beta and gamma are not required, they're false. Now let's have a look at the second equation, the double exponential smoothing. So this is our equation for double exponential smoothing. So we had to model, we had to smoothen both the level and the trend. So for the level we had a smoothing parameter alpha, smoothing factor alpha, and let's not worry too much about the entire equation. And another smoothing factor beta to smoothen the trend. So basically bottom line, in double exponential smoothing we had two smoothing parameters. And so now when we're doing it in R, here's our Holt-Winters in R. So now this hem diameter has a random part, the random fluctuation that is there in any time series, and it has a trend part. So we need two smoothing factors, alpha and beta, to smoothen a data. Alpha to smoothen the level and beta to smoothen the trend. So alpha to smoothen the random fluctuations and beta to smoothen the trend. So here we still say that gamma is false, and gamma relates to the seasonality. So our data still doesn't have seasonality, we don't need gamma. So that's a point that needs to be noted, and perhaps it's fun correlating with the background section where we talked about the three different kinds of equations to deal with three different scenarios. Anyway, so now that it should be clear that we use Holt-Winters and we are using it for double exponential smoothing to smoothen both the level and the trend, and we store all the forecasts in our skirt series forecasts vector. So the next step, let's have a look at what our Holt-Winters has done. So it has used an alpha of 0.8 and a beta of 1. So you remember the ranges of smoothing parameters. We have talked at length about it when we discussed alpha, that is smoothing the random fluctuation. So if it's closer to 0, it's totally smoothed. If it's exactly 0, it's totally smoothed. If it's exactly 1, it's not smooth. We did mention that practically we'll try to use between 0.1 and 0.7, but closer it is to 0, the better smoothed it is. But that said, the closer to 0 it is, it places less importance on the more recent data. The closer to 1 it is, it places more importance on the more recent data. And we did look at the graphs of this, right? Like 0.1, the plot is really smooth. 0.7, the smoothened data kind of looks like the actual data. Whether that's good or bad depends on the data. And that's what are we going to see in a current example. So if you look at a current example, this hem diameter, here's the hem diameter. Like no one on earth would wear as big a hem as this today. People will laugh at them, man. Like how can they go out on the road? So our data, our model should resemble the more recent data more emphatically. And if you look at the output from Holt-Winters, that's exactly what it did. It chose an alpha close to 1, it chose a beta exactly 1. So basically alpha and beta close to 1, what it does, it gives most importance to the most recent data, because no one wears big hems anymore, and Holt-Winters knows it so well. Wow, this function's amazing, man. So now you know how to interpret this. You can have a look at alpha and beta and see if Holt-Winters is doing well or not, right? It shows alphas and betas close to 1, which sounds perfectly reasonable for this data. So moving on, what did I say about Holt-Winters before? Well, the first part is about, so we have made a forecasts. We have made a forecast, we need to check the accuracy. But Holt-Winters by itself can only forecast for the in time part, that is for the period for which the actual data exists, for which the function has been fed the data. So you have this variable SSE, the sum of squared errors. You can print that out, and this is stored in the vector where you stored your forecasts. You can print that out and have a look and see if it's too big or too small. And this will make more sense if you like vary other parameters. But anyway, you can have a look at it and see how your accuracy looks like, in time accuracy. But a more practical approach will perhaps be just go ahead and plot your forecasts. So skirt series forecasts, again, like here, that is where you store your in-time forecast. Holt Winters can only do in-time forecast. So now here, the black line is the actual line and the red one are the forecasts. And just a quick look tells you that the red and the black are kind of close to each other. The red line does increase when it should have increased, and it has fallen down when it's required to decrease. So basically the red and the black overlaps, so the forecasts, the in-time forecasts are good. They're in the same ballpark. Holt Winters is doing an amazing job. Now we move on. We need to look at the out-of-time forecasts. That is the forecasts beyond the time period of the actual data. And what function do we need for that? The forecast function. You are already familiar with it. So forecast.Holt Winters. You feed it in the model or the smoothened data from the skirt series forecasts vector. What is this H for? This H tells the forecast function to forecast for 19 more years beyond the actual data. The actual data ended in 1910. So the forecast function, now that we have told it to forecast for 19 years, is going to forecast for 19 years beyond 1910. And we stored this out of sample forecasts in skirt series forecasts too. So moving on, how do we know the out of sample forecasts are doing well? We plot them. We use the plot.forecast function, feed it out of sample forecasts, and we plot it. So what the plot function gives us back? It gives us the actual data plotted along the forecast. So this blue line is the forecast. What should we note? We should note that in the most recent time, this was the value of the actual data, and the blue line pretty much starts from there. Exactly the same point. So the out of sample forecasts are in the same ballpark as the most recent actual data. Most recently, or in modern times, people are wearing narrower skirts, and we can pretty well assume that they are not going to suddenly revert back to 1870s and stuff. Like, they're still going to keep wearing those narrower skirts. Like, no one wants to look weird, right? And the blue line tells us exactly that nobody is in a mood to go back to 1870s. They're going to keep wearing the narrower skirts. And if you remember, the orange section actually gives us the 80% confidence limit, and the yellow section gives us the 95% confidence limit. And if you want, you can just print out the actual values using the skirt series forecasts $2 fitted variable. I perhaps haven't printed it out for this scenario, but you can do that. You have an example of this from before. So you can do that, have a look at the values. But this plot tells us that the forecasts are in the same ballpark as the most recent actual data, and our out of sample forecasts are good. So next, two things to do. First, to look at the autocorrelations of the residuals. So the residuals are available in the residuals variable of the out of sample forecast vector. The vector in which we stored our out of sample forecast was skirt series forecast 2. The $residuals variable of that vector has the residuals. Then we use the ACF function and tell the ACF function go back 20 time points. So lag.max basically tells the ACF function how many lags to use. 20 basically in English means go back 20 time points, and here in the x-axis you can see the ACF function has plotted the autocorrelations for 20 lags, that is 20 points backward. And do you remember how we are going to interpret this? Well, the way to interpret is to look at the spikes. The spikes are the plots which go above or below the blue lines at the top or the bottom. Now, how many spikes we have? We are never going to consider the spike at lag 0. We don't care about it. Other spikes, yes, of course, there's a spike at lag 5, but that's just one random spike. If there were spikes, say from lag 1 through 5 or whatever, lag 1 through 10, and then the spikes declined, that is, if it was such that the vertical lines were crossing the blue lines, and it doesn't matter if it's crossing on the top or the bottom, for several lags, for say 1 through 10, and then they decline, then you would have been worried. But one random spike, nothing to worry. Our residuals are not autocorrelated, and if they are not autocorrelated, what the bottom line is, we do not need to smoothen further. What the Holt-Winters function has done already is good enough. Moving on, so the next thing to do will be to do the L-Jung box test, and this will tell us if the autocorrelations between the residuals are statistically significant or not. So you have the residuals available in this variable. You tell the box.test function in R to go back 20 time points, that is lag equal to 20, and tell the function to do the L-Jung box test. And what you need to look over here is again the p-value, the significance value. So if this is below 0.05, there's reason to worry, but in our example, it's above 0.05. So this statistic is not significant. What it tells us is that the autocorrelations between the residuals are not significant. That is, the residuals are not correlated. And if they are not correlated, basically they are randomly distributed, and if they are randomly distributed, the data has been smoothened and we don't need to smoothen anymore. Then the last part basically checks if the residuals, visually checks. We have done the L-Jung box test to test it statistically. We have looked at the ACF plot to look at it kind of statistically. But to visually test if the residuals are seriously randomly distributed or not, we first simply plot it out. We plot out the residuals available from our out-of-time forecasts. And we do see that they are randomly distributed, right? There's no specific trend or pattern in it. They're all over. They're rising and falling like according to a particular rhythm. And they're all over. If you cut a line from 0 across this plot, there are equal number of points above and below. So that basically the residuals are the error terms, and as I explained before, like if there are equal number of error terms above and below the 0 mean, the errors kind of cancel each other. And if the mean is kind of 0, it means that the average of the error terms is 0. So there is basically no error. And last but not the least, we really want to be convinced. We plot the histogram of the residuals using the hist function. And this tells us, first, the mean is 0 of the residuals. Very consoling, because if the mean is 0, overall there's no error. The positive errors and the negative errors are cancelled out. And it tells us that the errors fit bell curve, that is, there are equal number of errors above 0 and below 0. So if there are equal number of positive errors and negative errors, the number of positive errors is equal to negative errors. So overall, it's boiling down to the same thing, that the errors are randomly distributed and the overall they cancel each other out. So we have traversed through the second scenario, and we have seen that Holt-Winters is doing a great job. Our data had a trend. It was increasing historically, but in modern times it has come down. Holt-Winters has used an alpha to smoothen the alpha of 0.8 to smoothen the level, and beta of 1 to smoothen the trend. These two smoothing factors being close to 1, we know that the more recent data is more important, and which indeed it is. women are never going to wear skirts with bigger hems, wider hems anymore. So Holt Winters indeed is smart and doing a great job. Next, we try to objectively convince ourselves that the forecasts are good. Holt Winters just forecasts for the in-time period. SSE tells us how accurate those in-time forecasts are. We plot out the in-time forecasts and we see that the in-time forecast, the red plot, is overlapping with the black actual data plot, which is very consoling. Next, we do the out of time forecast for 19 periods, and then we again plot the out of time forecasts and see the out of time forecast is in the ballpark of the most recent actual data. That's very consoling. We look at the autocorrelations. There are no significant autocorrelations. There's no significant number of spikes. We do the Box-L-Jung test. The p-value is higher than 0.05, so autocorrelations between the residuals are not significant. We plot the residuals to see if they are randomly distributed. If they are normally distributed with a mean 0, yes, they are. And finally, we plot the histogram of the residuals, and that conclusively tells us that the mean of the residuals or the error terms is 0, and there are equal number of positive and negative error terms. So overall, the error terms of the out of time forecasts also cancel out, and hence QBD, we can conclude that we have done a great job using the hem time series data to forecast future hem diameters. And in the next lesson, we are going to finish off the last scenario where we are going to handle seasonality.